In this lesson, we're going to set up our character controller script, this time moving our player 1 character using physics, right? But before we move forward, I want to just do a little quick setup. First, tidying up our and setting our folder structure. So here with our assets, create some new folders. So make one for characters. And in there, we will create folders for our cheesehead and for eyeball and just stick that in there and create a folder for scenes. Although we'll only have one scene, but just good to be in the habit of cleanliness, being neat and tidy. And also for scripts, we'll have folders for player. Just for now, we'll just do player, tests, and world, and put the test script here in tests. And we're not really going to need it anymore, so should remove it from our cheese head, or else it'll just get in the way. All right, so this time what we're going to do is we're going to start out with the input manager, mapping our user inputs through the input manager as opposed to using the get key method as we did before. So we'll go right to the input manager. So go to project settings input, and we'll set up the following axes that we'll need. We'll start off with 2 for horizontal motion and jump, vertical motion as well. So make that 2. And some of it's already predefined here. We'll just leave these predefined settings. Actually, all of it's predefined. We don't really have to change anything there. So for vertical, well, we'll just call this jump to make it explicit what it does. And we'll set the positive button to the space bar. So you have to type in space. There's no negative button. And for there's also no alternative negative button, but for the alternative positive button, we'll allow mouse clicks. So mouse 2, which I think is the middle mouse. Well, we'll see. And so we'll create a character controller script now. So go to the player folder in the scripts folder and make a new script called player controller. And we'll attach that right away to the cheesehead game object. And we'll start off by setting up a few fields we're going to need. So rigid body 2D, call it cheesy body. This will give us a reference to the rigid body 2D component. Float horizontal motion. This will get the for the input manager, it will that we just set up for horizontal. It will return a float. If you're using an analog stick, which we aren't, although you could set that up with a gamepad, nonetheless, it will return a float. With the analog, it will be maybe a non-whole number, but in this case, it'll be basically, even though it's a float, it will be a whole number, either -1 or 1, or 0 if there's no motion detected for the input. And we'll store that to a local float called horizontal motion. And we'll also have an int for move speed. And we'll just assign those with initial values in the start. Move speed, say 3 for now. We'll tweak these maybe later to get just the right values for character speed. Then cheesy body, we'll just use the get component to grab the rigid body 2D. So now we'll use that horizontal motion field to store the result of our input. So that's going to be input.getAxis. Now this would return a float of a varying amount if, again, you're using something like an analog thumbstick, but we're not using any analog control. We just want a whole number value. It's going to be digital, basically. So we'll just use the getAxis raw variation of this method, which just even if it's a small, even if it's a float value between -1 and 1 that's returned, it'll just return the whole number value equivalent. So I guess 0.5 will round up to 1, and -5 will round to -1, and otherwise it will just stay at 0 for idle, basically. So getAxis raw, and we'll pass in the string that refers to the input manager axis that we're referring to here, so that's called horizontal, and we'll just assign the value that comes out of that to the horizontal motion field. Now we'll say if horizontal motion is not equal to 0, in other words, an input has been read, we'll first use it to determine the orientation of the player 1 character. If it's on the right side, because the input it returns 1, we'll set the local scale to 1. Otherwise, if we press left, it'll be -1. We'll use that to set the local scale to -1, which will flip the character to the left, facing the left side. So we'll say transform.local scale, not Euler angles. Local scale equals new vector 3. We'll pass in the horizontal motion and leave the rest of the scaling unaffected. And now to actually have this impact the rigid body, we're going to use, of course, fixed update, right? So void fixed update. And we'll assign to the cheese body velocity, we'll say new vector 2. We'll pass in horizontal motion multiplied by move speed. And because we're not concerned with setting the y-axis through input, we'll just pass in whatever the rigid body's existing y-axis velocity is. And notice here how, because we're working with physics right now, with the physics engine, we don't use time.delta time. Doesn't really make a lot of sense, so we didn't have to multiply any of this to make sure that it has the same perception of speed regardless of the frame rate, right? We don't have to do that because we're using physics. So I'll just quickly test this out, make sure it's set up right. Yep, see, in the local scale changes depending on if our input returns -1 or 1 from the getAxis raw input method. Right now for jumping, let's go back to our script, and we'll need another field. We'll call it a bool jump activated. And in update, we'll grab this input for the jumping mechanic. So below here, we'll just have another conditional. If input dot, we don't need to get axis because we don't need a number return, so we'll just use get button down, and that'll grab the relevant button from our input manager just as well. Jump is the name of that button. If the jump button is pressed, set the bool to true. And then in fixed update, we'll simply have a conditional here that says if jump activated. So if that bool is detected by fixed update as being true, then we will use an add force, which goes back to what we looked at in the previous lesson. So we'll say cheesybody.add force, and it's going to need a vector2 force. So let's just say new vector2, and we're not going to be concerned with adding force to the x-axis, so we'll just pass in the existing x-axis velocity, and we'll add force, we'll give it 6. And there's an optional argument here that I'll talk about more in a minute, called force mode. So we'll say force mode 2d.impulse, and we'll then switch off the jump activated bool, so that solves the problem again that we looked at in the previous lesson. So go back to that if you're not too sure of what we're referring to in this code. All right, fix that. Now we should be able to jump. Oh, but look at that, I'm still able to use that add force to jump as much as I want to. And of course, if I'm going downwards, the force relative to the downwards velocity is going to result in less of a jump. See, it's just kind of, it's more like an air brake effect. Anyways, we're going to have to fix that. But before that, I want to just briefly mention a bit of this, what this force mode is all about. So this is actually an enum. If I hover over that, it says enum, and it gives us one of two possible choices. There's impulse that we used here and force. So I think if you ignore the this optional argument entirely, I think it just defaults to force mode 2d.force. But basically the difference between these two force modes is force mode.force is kind of like a constant pushing sort of, occurring over successive frames, whereas force mode.impulse is sort of a single explosive force typically meant to be applied on a single frame. So that's why we chose this for the jumping mechanic. All right, so we can fix this issue of having infinite jumping basically, as well as being able to manage all of these different possible states that our character can be in by using enums for holding exclusive states. Remember my analogy of how enums are like buttons on a blender that only hold a single state, that exclude other states when it's in any one state? Well, here we'll make good use of this for holding exclusive states with enums. So, for example, you can't be both moving left and moving right, or idle, for that matter, at the same time. So we can use those exclusive states for one enum, and meanwhile have another enum for, if you're airborne or grounded, you can't be in those two states at the same time. So we'll go on down the line with all of these different states that we can have for our characters and separate them with different enums for each set of exclusive states. And what's great about this state keeping functionality is it's really easy to understand what's going on when you use the enum to sort of summarize the code that determines that enum state. If you didn't really understand what I'm getting on about, you'll see if you follow along. Enums will do a lot of heavy lifting for us as we move along here. So let's create a new script called player state to manage our different player states. And we're not going to need to attach it to a game object. You'll see why in a minute. We're going to do something a little bit special here that's different from the other scripts that we've been writing. So call this player state. So for our player state mono behavior, we're going to actually leave that for now and just create our enums in this script. So we'll say public enum horizontal for one state, for one set of possible states. So idle. And here we'll make use of the ability to assign numerical values for our enums. If you have to refresh your memory on enums, just go back to that lesson. I can't remember the lesson number, and all this will make sense. So moving left equals -1, and moving right equals 1. And then we'll move on to another enum that we'll need for vertical. We'll call it. And we'll be either grounded or airborne. Those are the two mutually exclusive states we can have for vertical states for a character. And we'll also make public enum direction facing, because that also might be important for summarizing in our code what direction our player is facing. So left, again, will you make use of these numerical assignments that we can add to the enum. Right equals 1. Right now, before we make use of these states, we need to incorporate them as fields within our main player state class, right? Which we'll then use as a sort of single axis point for the rest of our scripts to manage the state of these enums depending on what's happening in code. Now, the obvious way to do this is just to make these fields static so that they're easily accessible from anywhere in code, right? But I also want you to be able to see these states, particularly during testing in the inspector, but Unity doesn't allow you to expose static fields in the inspector. So to solve this, I'm going to take the opportunity to show you a bit of an intermediate to advanced concept, which is actually not that difficult to write in code, called a Singleton pattern. This is part of a topic called design patterns, which is pretty much way outside of the scope of what we're dealing with in this lesson. But basically, design patterns are just an accepted set of standards for solving coding problems. Programmers over the years stumbled on these common problems and solutions in code. They recognized these common patterns that exist throughout coding, regardless of programming languages typically, and sort of settled on accepted ways to going about solving these common problems. That's the basis for design patterns. Now, a singleton is a very common design pattern, especially in Unity. I think you'll see it floating around quite a bit in code out there. And basically, a singleton is a design pattern which ensures that you have only a single instance of a class that you're creating. That's pretty much it. It just limits the class instances of the singleton class that you create to 1. And another benefit when creating a singleton is usually to have this single point of reference by making the instance static, which allows outside scripts to easily access the singleton instance. In our case, we're going to make a singleton with a globally accessible static instance in order to get and set relevant player states. So we'll then be able to see these states in the inspector because those states aren't going to be static themselves. All right, so maybe a little confusing, the wording, but hopefully you'll understand what I was driving at when we start writing the singleton pattern here. So for a player state class, we'll need a property for the instance to hold the single instance that we're allowing for this player state class. So we'll say private static player state so this will be the backing field underscore instance, and then we'll say public static player state capital I instance, and then we'll have a getter. So for the getter, we'll say, this is kind of where the magic happens with singletons. So if the backing field is null, then the backing field will get a new game object, which will we'll assign the name of it in the inspector here, calling it player state. And we'll also, at the same time, we'll add a component of this singleton script, right? Player state. The add component method. And a getter isn't quite a getter unless you return that backing field. So if the backing field is null, we create the game object and attach an instance of this script to that game object. Otherwise, if that instance then exists after it's already done this, and we run the getter again by accessing the instance in script somewhere else, then we'll just return the static instance. And here we'll have, that instance will have a public, a horizontal enum, which we'll also call horizontal with capital H. C# is good about detecting when you're referring to the type versus the field name, like in this case. So hopefully that's not confusing, but it shouldn't be confusing when you're accessing it in code in your different classes as we move along. And we'll say same for vertical, public direction facing, call it direction facing. So yeah, as I mentioned, this gets instantiated when we first run the getter for instance anywhere in code, which is basically anytime we retrieve a field within the instance. So for example, when we do this in the player controller, we'll just say player state dot instance running the getter, and we'll set horizontal to horizontal dot idle to start off with. Maybe this will give you a little preview on the usefulness of how we will be using these player states as we move forward. Dot vertical is going to be vertical dot airborne, and direction facing is going to be direction facing dot right to start off with. I'll show you how that now creates that getter. When we run that getter, it creates that game object, player state. And from here, we'll be able to see our publicly exposed enums. Since these are not static themselves, we'll be able to see these when we're testing. So that'll be pretty useful. So yeah, probably the weirdest thing about singletons on first glance is that the class has an instance of it inside of itself. Right? It might seem strange that you're allowed to do this, but there's nothing preventing us from doing that in C#. So anyways, we could have chosen other ways to view our player states. Maybe it would have been more convenient to simply output it to the screen with something like the onGUI method. But I figure you already know how to do that. We did that in a previous lesson with our scorekeeping and so on. So I took this as a chance to show you a common coding concept. So don't let the peculiarity of it put you off too much. If you don't like how singletons appear and how they operate, you don't have to use them, right? It's just an option that you'll see often, and taking this opportunity to show it to you. All right, so now let's make use of these states in the player controller. So here, when we flip our local scale, depending on our motion, we can set the player state for a direction facing enum to is going to be somewhat different than maybe you're expecting. So what we'll do is we'll do this. We'll take the horizontal motion and then we'll cast that numerical value, which is either 0, -1, or 1, we'll cast it to the enum direction facing. And that works. That can set our enum state. Again, because of this handy little option to have a numerical equivalent for our enum. All right, so to fix the infinite jumping problem that we had, we can just, right here, we'll just say if cheesybody.velocity.y is equivalent to 0, then player state.instance.vertical equals grounded, vertical.grounded. And now here where jump activated, that conditional is, we'll have an added conditional within that to make sure that we're first grounded before we're actually allowed to apply that add force. So if player state.instance.vertical is grounded, then we'll allow the add force to be applied, and we'll set also the state, player state.instance.vertical, we'll set it to airborne now. And we're not really going to use this, well, not anytime soon at least, but may as well set that horizontal player state here in the update. Again, using that casting functionality that we saw before. So we'll just take the horizontal motion this time and cast it to horizontal enum. Terminate that. All right, so let's just see how this all looks in when we press play. So let's watch our little states here as we're playing the game. Wait a second, something's wrong. Not sure I made that error. Vertical dot grounded. I'm sure you saw that before I picked up on it. So, all right, so once again, we'll test this out. Keep an eye on our different states. Yep, can't jump unless I'm grounded. And well, not much going on in the game, but it's a start. So before we wrap up here, let's just refactor this a little bit. Just wanted to get this stuff out of fixed update. There's not much going on there, but just to make it obvious as to what's happening, let's create a couple of private methods to hold this functionality. So private void walk motion. And for that, we'll just take that one line. That's all we need. And call that here, walk motion. And for jump, for this, say private void jump motion. And call that here.